Hey, it's Jim, and this is FRM Part 1, Book 2, Quantitative Analysis and the Reading on Machine Learning Methods, Part A. We've decided to divide this reading into two parts, A and B, so look for Part B recording soon, and hopefully you learn enough in Part A that you'll want to watch Part B. When I was going through this reading, I was tempted, and maybe you are too, to think of this as just a continuation of our understanding of classical econometrics theory. And while that might be true, there's much more to machine learning than just kind of a natural extension. Let me give you just a quick, maybe even a silly example to explain my thoughts here. In 2023, those of you who are NBA fans will note that LeBron James is most likely going to surpass Kareem Abdul-Jabbar as the all-time NBA career scoring leader. But let's suppose that we're really, really good and deep NBA fans, and we want to ask the question, which one of these two supremely talented individual basketball players achieved their scoring record in the most efficient and perhaps most effective, and maybe even some other kinds of ways? Let's further assume that somebody out there, not you or me, because we don't really want to spend all this time, but somebody out there watches every minute of every game played by these two guys, and they record all sorts of data, like LeBron's running down the court, he does a V cut and goes this way, we record that. Kareem gets the ball, he fakes one way and does a sky hook. We record that. And we record all of these different things, these different input variables. How many could there be? Maybe 1 trillion of these things. And so if we were using classical econometric theory to use maybe regression analysis, we would do some stuff and then we'd probably want to compute a standard deviation and then probably a standard error. Do you guys remember what the formula for standard error looks like? It's really just some kind of a standard deviation divided by the square root of n. So what did I say a moment ago? N is 1 trillion. Take the square root of 1 trillion. Anybody know what the square root of 1 trillion is? Well, I got my calculator out and I did it. It's 316,000. So when you divide by 316,000, what are you going to get? You're going to divide, and so it's going to be this really, really small number, which just throws off all of the hypothesis testing. That's where machine learning comes in. Machine learning allows us to process all kinds of massive amounts of data without the restrictions of regular old classical econometric theory. And there are huge amounts of applications for machine learning. One of my favorite is this image recognition. I think I've said to you guys before, I'm a voracious reader. I love reading spy novels. I love Jason Bourne. I love James Bond. And in the most recent novels that I read, The Gray Man, clearly you guys, hopefully you've read those books and watched that movie, but there's this facial recognition. So if you're a secret agent spy and you're going through the airport, you have to walk around like this so that you can't get captured, because they'll say, oh yeah, hey, there's Jim. He's no longer a secret agent spy. Let's go get him, or do whatever it is that secret agents do. So image recognition, medical research, game theory and game playing. I have 3 sons, and it seems like all they do is play Fortnite and Overwatch. And so clearly there's some machine learning in the algorithms for those games. Now, of course, I'm pretty sure Fortnite is not going to show up on the FRM Part 1 exam. However, you may have questions on applications like asset allocation, maybe option pricing, maybe stock selection, maybe, especially for those of you who work in the financial services industry, in financial institutions, you might have a question like, hey, how can we predict whether or not a loan will default? Or how can we predict whether a customer who invests in a massive jumbo CD will want to redeem that early? Or you can imagine all of the applications here. So where we were limited in classical econometrics with regression analysis and variances and covariances, I don't want to say all that goes away, but a lot of it goes away. Of course, we have some extra problems and some unique problems to machine learning, and we'll go ahead and talk about those. And you'll see that in the first 4 learning objectives, we'll do the remaining learning objectives in part B. So boy, I gave you just a brief summary of the philosophical. We'll do some practical differences here in machine learning techniques versus classical econometrics. There are a handful of machine learning types: unsupervised, supervised, and reinforcement. We'll do that here. We'll talk about principal components and k-means. I want to go back to the differentiate among those 3 types of machine learning models. I think of my role as a parent, my father's role as a parent, and then maybe my wife's role as a parent. Clearly, my father was a supervised parent. He would say to me, son, I'm going to allow you to go out tonight, but I don't want you to do this and this and this and this, and you can learn from just a little bit. So this was really restrictive supervised learning. My wife and I, on the other hand, we're probably a little bit more unsupervised. We say to our children, you know what? You may face these kinds of risks and obstacles out there. Make sure you use your brain. And then reinforced learning models. These are really cool, because what you'll see in a later slide is that in this slide we throw in a blue box. I think it's a blue box. And that blue box is some kind of a dynamic environment. And so this is super important for us as good risk managers, because what happens? We know that risk changes. I mean, think about this. If we have this model that was applicable for 2000 and 2003 and 2005 and 2007, and then all of a sudden we throw in the dynamic changes in the economy with the 2008 financial crisis, and we want to know, can this model, reinforcement learning model, can it be reinforced? Can the agent, we're going to call this thing an agent, can this agent learn from the changing and dynamic environment? So this is really, really cool stuff. You might be tempted as you're going through this reading to think that it's a little bit complex, but I don't think it is. It's really quite straightforward if you break it into its component parts, which is what we try to do, as always, in our slide deck. So let's go ahead and attack that first learning objective. And let's start over on the orange column, classical econometrics, because we know this. A solid foundation, right? We say something like, hey, you know what? If Jim, as a 61-year-old college professor, comes in and wants to borrow $40,000 to buy a car, Jim has a job, he's been a college professor for 100 years, he makes a good income, he has all these assets. The probability that Jim is going to default is super low. But if Jim comes in with his 24-year-old son, who's just recently graduated from college and just has his first job, if the son wants to borrow money, then that's a completely different kind of a story. Now, hopefully my son would have a low probability of defaulting, but clearly his probability is higher than mine. So we have to have some kind of a solid theoretical foundation in order to implement a model. And that leads us directly into a hypothesis, like the null hypothesis. Jim will not default on his loan. The null hypothesis, Jim's son will not default on his loan. Now, what we assume in this regression analysis is there is a linear relationship. And what we can say is that some of these variables over here cause the actions of some of these variables over here. I mean, clearly, if I lost my job and I lost my assets for whatever reason, and I lost my retirement, think squishing retirement accounts during COVID. I'm not sure squishing is a finance word, but you get my point. Now, machine learning, on the other hand, is kind of like this classical econometrics, but without all of the constraints. When I think of these constraints, I go back to one of my favorite movies, and I don't ever want to watch it when it comes on TV because it gives me nightmares. You guys ever watch Silence of the Lambs? Clearly Hannibal Lecter is substantially constrained. Now, we don't have that level of constraint in classical econometrics. But then with machine learning, well, what do we have written there? Little prior knowledge without human intervention, large numbers. Oh, and here's an important one: non-linear relationships. I mean, clearly, how many relationships are linear? In fact, I was just teaching my derivative securities class this morning, and we drew the graph for the payoffs and the profit for holding a call option. And so we clearly decided that there's a linear relationship between, dollars on the horizontal axis and dollars on the vertical axis. But with machine learning, we can throw everything in there. Like my silly example with LeBron and Kareem Abdul-Jabbar, by taking into consideration maybe the arc on LeBron's shot versus the arc on Kareem's shot. Number of three-pointers. I mean, how many three-point shots has LeBron taken in his life? I don't know, maybe 1 million. Probably not 1 million, but tons and tons of these things. But I wonder if you guys know how many three-pointers Kareem made in his life. I looked this up, obviously. I would never have known it. Kareem was 1 for 18. So you get this sense that you can consider data that doesn't fit into the Hannibal Lecter constriction under classical econometrics. Over these slides, I always, refer to movies, and I say, go watch James Bond and Jason Bourne and Jaws. I am not recommending you go see Silence of the Lambs if you haven't, because it will totally freak you out. It is a great movie, though. All right, how about a simplified machine learning approach? So how are we going to do this with, image recognition? How about security selection? How about deciding whether or not Jim is going to default on a loan or not, or game playing in a video game, or some kind of chaos theory? So over on the left hand, look at the first blue box. We study the problem. So we say something like, we want to know if LeBron or Kareem was more efficient in scoring all of those points. So then we have all this data up there. So look at that data. Oh my gosh. So the reading has a super cool section on how do we scale the data? How do you turn the arc on LeBron's jump shot into some scale where we can relate that to Kareem's bounce pass for a layup to Magic Johnson? How do we scale this stuff? Well, the reading gives us 2 methods to do this. You probably know how to do this already, so let me just do it quickly here. So there's standardization, where we take some numerator, some metric, and we divide by its standard deviation. That's known as standardization. What we can also do is normalize the data. This is called normalization. And so all we do there is, instead of dividing by standard deviation, we divide by the difference between the min and the maximum. And so you have a sense that in the denominator, in scaling the data and making it presentable so that the machine can actually learn, you have to have it in at least commonality of the base. So you do that either by standardizing or normalizing. And in the denominator, you're really trying to kind of get a measure of dispersion, right? Standard deviation is a measure of the degree of error. Max versus min is a measure of some measure of dispersion. So look at that middle box then. We have this machine learning algorithm in there, which, and by the way, I have no training in this, and I may not be smart enough to do this. I bet some of you, maybe many of you, are smart enough to go ahead and write the code. I'm clearly not. So we have this algorithm in which we say something like, all right, let's try to figure out how do we measure efficiency in LeBron's basketball game? How do we measure efficiency in Kareem's game? And so we have all these lines of code in there for this algorithm. When I was in college thousands of years ago, we used to have an if-then statement. And we have to type it out on cards and run it through an IBM computer. It took so long. I mean, it was so depressing to do that stuff. Nowadays it goes like this. So then what do? We have some output and we have some solutions that might say something like, oh, Kareem is way better than LeBron. and we say something like, all right, what is the output? What does it look like? Notice there's a little frowny face down there. So we need to figure out what we did wrong by saying Kareem is way better than LeBron. Well, maybe it's because we put too much emphasis on the sky hook that Kareem used to make. I mean, he had so many points using that sky hook because nobody could defend him. I don't know how many points LeBron has on a sky hook. Probably not many. So then we study the problem again and we do some stuff and then we do it again until we're done. Notice the smiley face up at the top there there's the launch. Now, note that it's our responsibility to understand all that stuff in the classical econometrics model, but it's not our responsibility to know all that stuff inside of the algorithm. We need to know what we want to train the algorithm to do, like measure efficiency, but we don't need to know all that stuff that are inside of that box. Useful in the following situations. All right, so I gave you some examples, like image recognition and asset allocation. So let's go ahead and see exactly what the reading says. This might be a good exam question. Customized or extensive sets of rules. Remember, I just got done saying, if then. Well, suppose you had 100 if thens. If Jim loses his job, then he defaults. But suppose that we have some strata inside of that. Suppose Jim only gets a 1% raise and he was expecting a 3% raise. How about if Jim experiences a 2% drop in his salary or a 5% drop in his salary? You see how you can have this extensive sets of rules to determine whether or not I'm going to default. Complex problems. I happen to think that the LeBron-Kareem example is way more complex than just the simplification of how I presented it to you because of those trillion data points. Traditional approaches are not as effective. We've done this. Dynamic environments. This is what I was saying earlier about let's throw the 2008 financial crisis in there, or let's throw COVID in there, or let's throw massive inflation in there. Adapt to new data. And then large amounts of data over on that far right. That should make perfect sense. Let's go ahead and complete our discussion on this particular learning objective. You might remember that every once in a while I asked you to get out your phone. I think this is a good slide for you to take a picture. So take a picture of that, click, and let's just quickly go through this. This kind of completes the slide that we started a couple of moments ago. So let's go ahead and start over on the right-hand side. Classical econometrics identifies and estimates that relationship and it tests the hypothesis. This is well-structured, clearly defined, independent and dependent variables, right? We're assuming normal distributions and linear relationships, and these models are going to be based on their ability to interpret these relationships. So we know all that stuff from our old-time knowledge, but now let's go ahead and look at the middle column there, machine learning techniques. And notice what we've done down the left-hand column, goals, data requirements, assumptions, and interpretability. And so these are probably 4 really good exam questions. What does that learning objective say? Difference. So what are the goals and data and assumptions differences, right? So the machine learning can learn from the data and continuously improve. But here's the important thing. You do not need to specify the relationships between and among all of the variables in advance. And it can handle large amounts of unstructured data. So over in classical, we've got this structured stuff. When I wrote my dissertation, I collected data on, I can't even remember, maybe 200 different companies who had classified board provisions in their model to elect board of directors. And so I had 200 of these, well structured. I had a defined variable, and then I did some regression stuff. But over in machine learning, I could have had those 200 plus 2,000 more, or maybe 200,000 more, and I would not have had to identify the relationship beforehand. I could just throw it in there and say, you tell me what's important, rather than me trying to figure out the economic and theoretical underlying assumptions and theory that will determine whether or not the model is acceptable. Nonlinear relationships. So I think that's probably an important one. It might sound like a simple question, but make sure you know linear versus nonlinear. And complexity. So we did all that. All right, so let's go ahead and go back to that second learning objective: unsupervised, supervised, and reinforcement learning. All right, so unsupervised learning. What are we doing? We are just taking this data set and we're throwing it into the algorithm, and we say something like, hey, you figure it out. I tell my students this all the time when I give them assignments. We have, in my investments class, I have them craft a fictional client, and then we write a policy statement for that fictional client. And they come to me and say, "Oh, Jim, what should I put here? What should I put here?" And I just say, "You figure it out." And that's what we're doing here. Unsupervised learning without a teacher. Notice that this algorithm is going to recognize patterns and waves and relationships without any kind of an explicit target. We're saying something like, you figure it out and you find what's important. And we do this a couple of different ways. We do it in clustering, which we'll talk about in just a little bit in more detail. We'll talk about dimensionality reduction, which we'll talk about in just a little bit. So with clustering, think about a graph where you have, a whole bunch of data points all the way in there, and you try to find clusters. And so essentially what you're doing is the machine will just randomly pick a point. It's called a centroid. And it will say, all right, let's go ahead and suppose that this is the center of a cluster. And what it will do is it'll calculate the distance between that center point, that centroid, and each of the people, each of the data points around it. It'll calculate the distance, and it'll try to minimize that distance. And if there's a group of observations that fall within some reasonable distance, that will be a cluster. And then there might be another cluster and another cluster. And so we need to figure out K clustering. How many Ks are there that we can group into clusters? And so if we can cluster like, hey, these people here, they have a 0% chance of defaulting on their loan. These people over here have a 5 to 10% chance of defaulting on their loan. And these people up here, they have a 100% chance of defaulting. Imagine having that information when you have a new client who comes in and says, I want to borrow $40,000 to buy a car or whatever it is. You have this clustering, and you can say to this person, hey, you fit into this cluster. Therefore, I'm going to charge you an interest rate based on this particular cluster. Oh man, this is such valuable information. Now, dimensionality reduction it's similar, but it's different in the fact that we have all these dimensions. So think of a dimension as different than a cluster. Think of dimensions as maybe factors. What we want to do is try to identify these unique factors that help us lower the dimension, lower the distance. We're still doing distances here. So these unsupervised things, these are really cool because you don't really have to do a whole lot of work. Now, I say that, and I know many of you use this kind of stuff in your work, in your jobs, and I know you work really hard. So I wasn't discounting that at all. Examples: principal component analysis there in the middle. We'll do that. K-means, we'll do that, and then association rule learning. We'll do all that kind of stuff. So what we're going to try to do is we're going to try to take a training set like we have up at the top, and we're going to use that training set to estimate the parameters within side of that data set, whether it's by any of those three methods. Now, supervised learning is just a little bit different. It's given a labeled data set and it's instructed to make predictions. So here's a really obvious question on the exam. Back here, we're probably not going to make too many predictions based on the output of this model, although we can. We can do that, like my example that I just gave. Here we're coming out with a goal of making predictions, and that's super important. So notice the training set over here could be lots and lots of different things. They could be labels, they could be instances, they could be LeBron, they could be all sorts of things. And then what we're going to do is we're going to try to do something over here on the right-hand side of this arrow where we're going to evaluate a new instance, a new customer, a new training set, not a new training set, but a new possibility over on the right-hand side there. So look down at the bottom. This is a labeled training set for email spam classification. And so we're trying to figure out what is spam and what is not. I will say this, that my email provider is not really super good at identifying it has to be super spam. I mean, it has to come from XYZ627 at 337-1414 dot something for mine to forget about all that stuff. All right, types of supervised learning here. We have classifications, which is what I was saying just a little bit earlier about the LeBron and Kareem, and also the default or not default. So there we go down at the bottom, likely to repay or likely to default. And then of course, supervised learning, we can use some regression analysis in there as well. Some examples of supervised learning algorithms. These are really kind of cool things. K-nearest neighbor, decision trees, neural networks, and support vector machines. Some of these show up in the next reading, and we'll focus on them at some other date. All right, how about this third type, reinforcement learning? This is what I was telling you about earlier, and here's that slide. There's the blue environment change, but let's do this first here. So we have an agent. So this learning system is an agent. So just think of it, I always, what's that word where you give inanimate objects qualities of the humans? What's that called? Anthropomorphication or something like that. All right, so think about this agent. I always think about this as a person living inside of the algorithm where you're trying to get this agent, you're trying to get this person or this fictional person to follow a path and get smarter. Reinforcement learning. Of course, this is trial and error. And the classic example of this, of course, is chess, right? You play against the computer, the computer is probably going to win or lose based on how many trial and errors that agent has been through. Now, of course, let me give you another homework assignment. Have you read about the scandals that have enveloped the chess world in 2022? I mean, you can't make this stuff up about cheating and all sorts of non-G-rated stuff. So it's worth reading for just 5 minutes. All right, so what happens here? We get rewarded for desired behavior and penalized for undesirable behavior. That makes perfect sense. But what this agent has to do is interpret the environment and then make a perception about that environment and then perform an action. And so the result of that action is either, success or failure, right? Desired behavior or undesired behavior. And so that agent then learns from its mistakes or its successes, and then it keeps learning. And so this is a big circle. It's a big cycle. So look down at the bottom, maximizing the reward and minimizing the penalty. That sounds like a pretty good exam question. So here's a little bit more detail of a graph under which we throw this blue box of the environment somewhere inside of the distance between, here, let me go back here. The distance between the get rewarded and the perception and then the perform the action. And then somewhere we just throw this changes in environment. I just read a book where this secret agent knew that he was going through an airport and knew that there was going to be this image or facial recognition software. So he wore a wig and put on a big nose or something like that. I can't really remember. So that's the environment. Can the agent learn from changing environment. And so, of course, the penalty and then the rewards, they have to be reflective of that changing in the environment. You can't say something like, okay, the agent put on Spock ears to get through the airport, but left his or her face able to be interpreted, and so he was caught and put in jail. He or she was caught and put in jail. So the Spock ear. So you can't punish the agent for doing something and failing. You have to give the agent another chance, right? So then you go around. Let's just go back here. You just go around the loop, and you go around and you go around until. Now remember, this is going on hundreds of times, thousands of times, tens of thousands of times. So look at some of the applications down at the bottom. Portfolio allocation, security selection. This is what I was saying early on. Let's go back to our Harry Markowitz from 1952. What did Harry do? He told us that he could provide us with an optimal allocation of weights for our stock portfolio that minimizes risk at every given level of return. Oh, so Harry Markowitz, we can do this in Excel. I mean, I have my students in the investments class. I mean, we do it in 5 minutes. We can draw the efficient frontier. But how about if we throw in COVID, if we throw in hyperinflation, if we throw in the impending recession in 2023? You heard it here first. Of course, I read it in the Wall Street Journal first. All right, remember a few moments ago we were talking about this dimensionality, and so this is principal component analysis. So let's just go back to my silly LeBron and Kareem example, and let's say that we have some inputs. We take number of shots taken, distance of that shot taken, which of those shots were made. Maybe we could even evaluate the spin on the ball. We can evaluate the defense. Did someone have a hand up? Was there no defense? Was it a dunk? Was it a hook shot? Was it a foul shot? All right, so we do all that stuff. We have all of this data, and what we want to do is decide which ones are important. Which ones are most important? Principal component analysis. Does it really matter? Does it really matter that LeBron's spin on his ball is quarter of a revolution faster or slower than Kareem's? I don't know. Maybe it is, maybe it isn't. But principal component analysis will enable us to make that determination. So look in the middle, those boxes there. Simplifies complex data sets, right? It turns, what did I say? We had 1 trillion data points, so it turns the trillion into, I don't know, something that's more manageable. Burden of dealing with large data sets and improves the interpretability of these models. So principal component analysis, it's the most popular. Projecting a training data set into lower dimensions. Now, it's called a hyperplane. All that means is that the data set has been reduced. And what it does is it finds directions. Now look at that last, captures the most variance, right? So once again, we use this concept of dispersion or volatility or variability. All right, how do we do this? We standardize the data. We can standardize it, or we could normalize it. We don't have normalize in this box, but you could do that. Calculate covariance matrix. Oh, this was so much fun for me when I was a grad student. I did this, thousands and thousands of times. And then we want to select the top n principal components. So that n is the desired dimensionality. And then what we do is that we project the data onto that space by the n principal components. So we've taken this and we've gone to that. Now it's a little bit more subtle and complex than that, but you get the idea. And what we can do is we can just look at some kind of a plot to see how that variance is being reduced. And you'll see this here in an example. So let's suppose that we want to compare the very small cap 30 versus the diversified small cap 500. So we have 30 stocks here and 500 stocks here, and we want to see if we can use principal components to describe the returns. All right, so the data set, more than 1,000 technical and fundamental features. Now, here's the problem with regular old classical econometrics. if we have all of these variables, remember in classical economics, we're calling them independent variables, but it's likely that some of those are related, and that's going to result in multi-collinearity. So what do we do if we have tons and tons of multi-collinearity? I mean, there are things that we can do in classical regression analysis, but if we have 1,000 of these things, I mean, we're not going to be able to use classical regression analysis. So we might as well just throw that model out the window. Let's do principal component analysis. So we're going to try to create new variables that capture most of the variance. So here are two pictures. Over on the left, there's the small cap 30, and over on the right, there's the small cap 500. Notice on the vertical axis, the percent of variance that is explained by the number of principal components. So we're going to just say, look, all the way out at the end, what's that last point on the horizontal axis? Would you say that's 15? Clearly that's 15. So we can say that there are 15 components that explain 100% of the variance. Well, that sounds an awful lot like R squared back in the old econometrics classical regression days. But note that at 14 and 13 and 12 and 11 and 10 components, that those components pretty much explain 100% of the variance. So now what do we do? Well, now we keep going over and over. What do we see? Well, notice that it's a downward slope. Of course, it's going to be a downward slope. This is probably the result of diversification. So what do we find? We're going to try to find the point where the downward slope goes from increasing to decreasing, right? Well, clearly that's at principal component 4. So for both of these, we need, somewhere around 4 principal components instead of the original 15. You see how what are we trying to do? Reduce the dimensionality of our data set. So here are a couple of just conclusions from those previous two graphs. This was taken from a study, so there's 88% and 91%. My 61-year-old vision, I really can't see that, but you can see it's around 90% for both, right? Yes, very small after the 5th principal component. So we're probably going to just disregard. So let's go back here. What do we see? 4, we need at least 4, but we still have some reduction in variance at 5, and then at 6. 7 doesn't really do us any good. 8. So do we want 8 or do we want 4? Well, that's really kind of the artistry involved in principal component analysis. I mean, there's a lot of math, a lot of technicalities here, but there is some artistry. Clearly, 1 component is not enough, 2 is not enough, 3 is not enough. 4, you could make an argument that 4 is, but you could also make the argument that 5 is. It depends on, what you're studying and what kind of a confidence level that you are comfortable with. So look at that last one here. I think this is a great exam question where you would be given a graph just like this, and the question would be, what would be the result of principal component analysis? How many components do you think we should use? And there might be some other information in there that you would be able to say, 4 or 5. All right, let's go back to and finish our conversation on clustering. So think about this. You have this data set, and I was explaining to you earlier about the centroid, and what we're trying to do is we're trying to find data points that are close enough to that centroid so that we can call it a cluster. Now remember, this is all back into the unsupervised learning technique. And so all we're trying to do is minimize that distance. So look down at the very bottom point. Based on the idea of minimizing the sum of the squared distances, that was an important concept back in classical econometrics, between data points and the centroid of the cluster. And so typically what happens is that the algorithm will just take this data set and it'll just pick randomly a centroid and say, okay, here, let's start right here. But suppose we have the data. Can I do this? Suppose we have the data right here, and the algorithm, for some mistaken reason, picks a centroid way out here. You guys see my hands way out here, and it measures the distance, right? The sum of the square distances. Well, immediately the algorithm is going to say, boy, that was a stupid starting point. So what it will try to do, it does this randomly, but it can try to find the cluster initially, or at least some relative cluster before it even does all of this stuff. And so that random assignment will go somewhere. So look at the illustrations there. We have good clustering in the middle. We have poor clustering on the left. We have, are those three triangles on the bottom right over there? Is it better clustering? Or notice we put the maybe in there. It might be better clustering. And so what this k-means clustering algorithm will do is come up with how many clusters are in this data set. I mean, clearly, what would cluster analysis come up with in our LeBron versus Kareem example? Number of shots taken. That's probably a cluster. But probably number of shots made versus number of shots taken. Maybe that's a cluster. And then foul shots attempted. Maybe that's a cluster. And there's other different ways to do this with ratios and distances that you can come up with different kinds of clusters. And I was giving you kind of specific examples there, but they could be general as well. So here's a slide just on this process. I think I've been through this. Randomly allocate initial k centroids. So we randomly pick, 5 or 10 or 1. Assign a data point to each closest centroid, creating k clusters. That makes sense. And then take the average and reassign, what are we doing? Going back here. I'm just going to read the bottom to you again. Minimizing the sum of the square distances. So it really is just the algorithm getting a ruler out and measuring the distance between all of these trillion data points and then saying, okay, let's put this into a cluster. And this is into a cluster. Now, I was fascinated by this section of the reading. I've come across this just a handful of times in my life, the difference between Euclidean and Manhattan distance. And by the way, there is a question at the end of this reading on computing Euclidean distance and computing Manhattan distance. So I would know this. I mean, it's simple math here, but I'm going to give you a really fun example here. You guys know who Stephen Wright is. Stephen Wright is a comedian who did stuff, probably before you were even born, right? I'm guessing you guys are probably around 30 years old. But here's your homework assignment. Do not watch Silence of the Lambs, but go watch a 5-minute clip of Stephen Wright. So he says that this is when he was a little guy. He said, I was in math class one day when I was in the 5th grade, and the teacher taught me the straightest distance between 2 points is a line. Shortest distance is a line, right? So he said that night he had a baseball game and he got on first base. So he was there and he stole third. He just went right around second. So that is super funny stuff. So that's the Euclidean distance, but the Manhattan distance is going to second base and then going to third base because those are the rules of baseball. By the way, the Manhattan distance was named after the Manhattan square blocks because you have obstacles in between 2 points. So there's the formula for the Euclidean distance down there in the bottom box. Here's a little illustration, Euclidean. So there's first base and there's third base. So Stephen was running across the pitcher's mound. And then there's the Manhattan distance. You'll never forget the difference between those two if you go watch. If you go listen to Stephen Wright. All right, so let me go back here. So there's the Euclidean distance. Notice we're taking the difference between 2 points and then squaring, and then taking the square root. But for Manhattan distance, all we're doing is taking the difference between 2 points and summing those. And those are along the grid lines. Let me go ahead back here somewhere. Oh yeah, here it is, that fourth block point. The Pythagorean theorem, the unknown side of a right angle triangle. I'm guessing you guys remember that from high school or grade school or kindergarten, whenever you learned that. So let's do a quick example here. And I would know this because Well, it was at one of the questions at the end of the reading. So here we have three companies, P, Q, and R, and we have data on market cap, PE ratios, and debt to equity ratios. So look at the bottom there, calculate the Euclidean and Manhattan distances, companies P and Q. So let's go ahead and do that right here. Well, all we're going to do is take the difference between those 2 points and square it. So 0.5 minus 2.5. So let me go back here. So there's 0.5 market cap minus 2.5 for P and Q. Everybody see that? We square it and then we add, and I'll just go back real quickly. There's 9 minus 15 and then 0.6 minus 8. Square all that, take the square root, and you get 9.73. For the Manhattan distance, you do the same thing. I mean, notice that it's 0.5 minus 2.5, but we're gonna take the absolute value of that and we're gonna sum those, and we get 15.4. So of course, the Euclidean distance when you go from first base to third base is shorter than if you have to go to second base. Now, this is really a fascinating part of the reading. There's really not a lot of information given in here about performance measurements, but what I got from all this is there's a measure of inertia, and there's the formula there. What we're doing is we're summing the distance squared. So these are, we're getting a ruler out and we're measuring the distance, and that's called the inertia. And what this algorithm will do is it tries to minimize the inertia. So I don't think, and there are no questions at the end of the reading about computing inertia, but notice that we've been so kind enough to put it into red at the very bottom of this slide. Lower inertia means the best clustering. So I think that is the very likely exam question if it shows up. Now remember, the reading doesn't emphasize this a whole lot. There's some things in there that, you have to be prepared for almost anything in these readings. So I would know that lower inertia means best clustering. Yeah, so what do we try to do? We try to say, we want 3 clusters or 10 clusters or however many it is. If we set those clusters as too high, then it's too specific and it might not reflect everything that's going on between and among all those variables. And if K is set too low, it's probably too general. So this is really extremely important, is trying to figure out the appropriate, or even, dare I say, the optimal value for K. Now, one way to do that is to look at the elbow method. And those of you who are sports fans and football fans will know that an elbow injury played a key role in Super Bowl teams. All right, so look at the plot here. We're going to take on the horizontal axis the number of clusters. And then we're going to go back, look on that vertical axis. So we're going to call that this within cluster, right? So inertia, what do we want? Well, we're going to try to find that elbow point where that inertia decreases more slowly. Think of it as kind of like an optimal value of K. So what did I say back here? We were worried about K being set too high or K being set too low. So this is kind of similar to the principal component analysis that we just did, but we have a different horizontal and, of course, a different vertical axis. And so this is a perfect exam question to find that elbow point. Now, I'm guessing that on an exam, it would be fairly obvious. If it's a straight line going down and they ask that question, well, then just pick B and move on with your life. But clearly, there has to be a non-linearity in the relationship. And so I'm guessing that they would make it a relatively obvious notion. Now here's another, this is just a brief paragraph in here about this silhouette coefficient. The equation is not even in the reading, at least in this section of the reading. But what this thing does is it determines what's known as a silhouette coefficient for each value of the K. And this coefficient is measuring and comparing distances, just like we've been doing throughout this slide deck. And it's going to try to find the similarity with its cluster versus some other cluster. So I'm not sure you need to know everything there in the math formula. Just look at the red in the bottom. We've been kind enough to do this. The optimal value of K is the one that corresponds with the highest silhouette coefficient. So back here, what were we doing? We wanted low inertia and high silhouette. That sounds like something that you ought to remember. Let's go ahead and finish up this slide deck. What are some limitations? Boy, you need to specify clusters. So if we don't have any idea about the clustering, we're not quite sure. And then we're going to assume that these clusters pretty much have the same shape and that they probably have very similar sizes, maybe not identical size. So you can have a cluster like this and then a cluster like this, but you can't have a cluster like this and then a cluster like that. And that takes us through these learning objectives. So what I want you to do right now is I want you to go to the reading and I want you to just very quickly look through those, I think it's 14 or 15 questions at the end, and see if you can just work through them quickly. Now, after we do part B, I'm going to have you go do these with a little bit more intensity and veracity. So, hey, thanks for watching. I had a super fun time, and good luck studying.